Continuing, we're going to start looking at question 4.14, which is slightly different because 4.14, instead of asking for work, is asking about heat. So a saturated mixture of liquid water and vapor at 112.3 quality is initially contained in a rigid tank with a volume of 10 liters. Heat is then supplied to this mixture until its temperature is 150 degrees Celsius. Calculate the heat transfer required for this process. Okay, so because it's a rigid tank, we spoke about this, I think, in one of the tutorials. Because it's a rigid tank, there's no change in volume, and wherever you have no change in volume, you have no work done. And this will be important because to solve this question, we're going to look at the first law of thermodynamics and see what cancels out and what doesn't, so we can sort of better define what we really need to do here. So the first law of thermodynamics can be expressed Q dot being the rate of heat transfer minus W dot, which is the rate of work being done, is equal to the change in energy of the system in whatever way that may be. So what types of change of energy can we have? We can have a change in kinetic energy, okay? We can have a change in potential energy, okay, that's another one. And we can also have a change in internal energy. Now the thing is the system changing kinetic energy? No, it's just a rigid tank. It's not like things are flowing in and flowing out at some speed. It's just a rigid tank. Is it changing potential energy? Is the center of the mass of the system moving up or down? No, it's just, they don't tell us that. So we're assuming this tank is just standing still. So we have no kinetic change in energy. We have no change in potential energy. So the only thing we're left with is the change in internal energy, which is mu2 minus u1. And we already said that because it's a rigid tank, work is 0. So basically, we need to find U2 and U1 in each state to be able to answer this question. So it's really just a matter of doing sort of chapter 2 level stuff and identifying certain properties at a given state. Now we're told that state 1 is 100 degrees Celsius and 12.3% quality. Okay, so we know we're a mixture at 100 degrees Celsius. So let's have a look at what the internal energy might be here. Property tables. Nope, there we go. All right, so 100, good. I'm just gonna erase some stuff so it's a bit clearer and I can re-box it for you guys, if it lets me. There we go. Okay, so again, we're looking at this line over here, 100. And we know that we're 12.3% of the way between VF and VG, between UF and UG, HF, HG, SF, SG. Each of these properties, we're 12.3% of the way between them. So what properties are of interest to us here? Well, we know we want to find mainly the internal energy. Okay, so if we find the internal energy, we know we're 12.3% of the way between 418 and 2506. Now, interpolating between them, we've done this many, many times in the other videos, so I'll just write out the equation. But basically, U1, being the one we're trying to find, is equal to UF plus X UG minus UF, where UG and UF are these two values we boxed. Now, I'm not going to do it in front. I'm just going to grab the answer. But basically, if you plug all that in, you'll get an internal energy of 675.76 kilojoules per kilogram. But there's more, because we would also like to know the mass, or something about the mass of the system. So how can we find that? Well, we know the tank is 10 liters. If we know the specific volume, we can find it. So let's also find V1, which is exactly the same thing. Just instead of UF and UG, we're using VF and VG. And it's the same state, so it's the same quality. So X is still 0.123. I'll just write that here. So VF plus X times VG minus VF equals, and just again to show you where that's coming from, it's the difference between this guy and this guy, or well, it's 12.3% of the way between them. more accurately. And if you do that, you will get a specific volume of 0.2066 meters cubed per kilogram. And if we want to find the mass, all we have to do is take the volume of 10 liters and divide it by this, right? So if we take 10 liters, so I'll say mass equals 10 liters divided by 0.20, well, you have to keep the units consistent. So remember, a liter is a 10 centimeters by 10 centimeters by 10 centimeters. 2066 meters cubed per kilogram. So if you do that, you should find that the mass of the system is 0.04841 kilograms. All right, so this will be important later, but we're going to sort of put it on the back burner. What's really of importance to us is these U values for now. Because even without the mass, you could do this per unit mass. If you just divide this first law by m, you could do, instead of the absolute amount of heat transfer, you could find the heat transfer per unit mass. Okay, so where were we? Yes, finding U2. So because it's a rigid tank, we know that V1 is equal to V2. All right, so 0.2066 meters cubed per kilogram. And I'm just going to draw a line through here, because now we're looking for states 2. So V1 is V2. That's all good. We're told that the temperature is 150 degrees Celsius. So let's go see what U2 is in this state. If we go here, let's just see, maybe it's a mixture. If not, it'll be superheated. 150 is the V that we have between the right values. Is it between these two values? Yes, it is. It is. We have about 0.2. So we're still a mixture, but now we're at a different state. Good. But we don't know how far down the line we are in terms of our quality, right? So instead of using the quality to find our values right now, we're going to use our known value of specific volume to find the quality. And once we know the quality, we can find the internal energy by going that much percent of the way between these two values here. All right, so let's see what this would look like. Our quality is going to be equal, so X2 is equal to our specific volume, 2066, minus VF over VG minus VF. All right, and again, we've done this a million times, so I'm just going to give you the answer. It's 0.525. So 0.525. And now all we're going to do is basically this equation again, but using the new state values for UG and UF, and of course our new quality. So U2 equals, again, UF plus X, which is this guy now, times UG minus UF, where UG and UF are these new values of UF and UG for the new state over here. Okay? And if you calculate this, you will get U2. So U at the final state is equal to 1643.5. 1643.5 kilojoules per kilogram. And now we have everything we really need to know. We have everything we really need to know in terms of how much heat is being input to the system. We have the mass, we have U2, we have U1. So Q equals, again, I'll just rewrite it, well, with the numbers, I guess. Q equals the mass, 0.04841, times U2 minus U1. 1643.5 minus 675.76, which equals, if we do the math, 46.9 kilojoules. So to go from one state to the next, we had to add heat, 46.9 kilo. The few examples we've done in in chapter 4, you can see that to change the state of a system, one of four things has to happen, or any combination of these four things. But to change the state of the system, you have to go either do work to the system, allow the system to do work to you, give heat to the system, or allow the system to release heat or take heat away, however you want to look at it. But the point is, there has to be either some work or heat interaction or any combination of them. Okay, that's the only way that something can change state. So whenever you look at a change of state, you know that any one of these four things or a combination of them happened. Okay, in this case, based on the context of the question, we know there's no work interaction, right? But because the internal energy increased and because there is no other change in kinetic or potential energy, we know that the internal energy increased by identifying state 1 and state 2. We can see that it went from 675 to 1643. If there's an increase in energy, that means energy was added to the system, right? And we know there's no work that can be done to or from the system. So the only way energy can enter or leave the system is by heat. And if the energy of the system increased, that means energy was added to the system in the form of heat. In other words, heat was added to the system. The system was heated. Okay? So this is just so you understand fundamentally what's going on when we change states. It's a change, it's a transfer, an energy interaction, either work or heat or some combination. It can be to the system, from the system, done on the system, by the system. But this is what happens, and this is what the first law of thermodynamics allows us to see a lot clearer.